I found a chair, and I have a table now. This is progress. I haven't been able to find any food since I landed here, though. Anyway, I have some theories about what's going on here. It all has to do with entropy. Welcome to the Chemist's Codex. My name is Peter. I like to talk about chemistry and D&D and movies and comic books and whatever else might catch my interest. So, if any of that sounds interesting, go ahead and subscribe so you don't miss when I upload a new video. Now, for those of you who are confused, let me explain. A few years ago, I uploaded a video where the void appeared in the background. It only appeared in that one video before I kind of disappeared for a while. Grad school, am I right? Well, recently I found myself inside the void with no idea what happened. But I have some thoughts on that now. Like I said in the cold open, it all has to do with entropy. I'm assuming most of you have at least heard the term entropy before and probably have an idea of what it is. You might know it as disorder or randomness or chaos, and those are all fine ways to think about it, but they're not entirely accurate and can lead to some confusion. So what exactly is entropy? Well, that's kind of a tough question to answer. The answer I want to give is more so the story of three scientists, who greatly contributed to the development and our understanding of entropy and thermodynamics. Now, before I get too far into telling this story, I need to give a bit of context first, specifically how a heat engine works. In short, an engine is really just a piston that's driven back and forth. In a heat engine, it's driven through heating and cooling of some sort of substance, typically a gas, that's enclosed in a cylinder that's sealed with the piston. See, in the early days of thermodynamics, people were primarily concerned with how efficient we could make a heat engine. In fact, thermodynamics really came about because of the steam engine. The steam engine, as we think of it today, really came into being around the 1700s and was improved upon, and when the Industrial Revolution occurred, people were really focused on how efficient they could make one of those engines. Enter Sadi Carnot. Those of you who have taken a thermodynamics class before might have heard the term Carnot engine. Well, this is the guy that's named for. Sadi Carnot was born in Paris at the end of the 18th century. His father was a prominent member of the French government, holding office in the highest governing body at the time. Carnot was initially educated by his father as he prepared for the exam to enter the École Polytechnique, a school renowned for its instruction in math and physics. Carnot was admitted to the school at the age of 16, the youngest age they allowed. When Carnot was 18, he and his classmates fought in the Battle of Paris, the battle that led to Napoleon's first exile, and this appeared to be his only experience with combat. After graduating, Carnot was admitted to a school for military engineering, where he completed a 2-year course and became an officer in the French Army's Corps of Engineers. Carnot became a captain in the French Army's arm of engineering, where he was posted to many different locations, primarily inspecting fortifications and writing reports. However, his recommendations weren't really listened to, likely due to his father being a prominent member of Napoleon's cabinet. Noticing his career was stagnating at the age of 22, Carnot took leave to prepare for the entrance exam to the General Staff in Paris. Taking a lower rank of lieutenant, Carnot remained on call for military service but was primarily focused on private intellectual pursuits. It was here where he attended lectures on chemistry and physics and became interested in the efficiency of heat engines. These studies led Carnot to his work, Reflections on the Motive Power of Fire, his only published book. After publishing this book using his own funds to print about 600 copies, it didn't really receive much attention. After Carnot died at the age of 36, the book had pretty much faded into obscurity, practically disappearing from libraries and booksellers. It was only after his death that Carnot started to receive attention, and his book led to the establishment of concepts like absolute temperature and entropy. It's because of this that Carnot is often called the father of thermodynamics. At the time Carnot was studying heat engines, very little was actually known about the scientific principles that governed their function. The first law of thermodynamics hadn't even fully been established yet, and very little was known about what heat actually is. The central part of Carnot's book is a description of an idealized heat engine, what would later become known as the Carnot cycle. It starts with a gas cylinder enclosed with a movable piston. The cylinder is brought into contact with a high-temperature reservoir, allowing the gas inside to expand as it increases in temperature. The cylinder is then removed, allowing the gas to continue to expand adiabatically. This means that no heat is allowed in or out of the system, so the gas ends up cooling. The cylinder is then brought into contact with a low temperature reservoir, allowing the gas to compress as it decreases in temperature. The cylinder is then removed from the low temperature reservoir as the gas continues to compress, again adiabatically, which means that it will increase in temperature this time, returning it to its original temperature and thus closing the loop. The important details about the Carnot cycle is that, one, it is completely idealized. There is no friction, there's no transfer of heat between any of the components, there is no wasteful process whatsoever. And the second important thing is that it's reversible. Carnot understood that this cycle could give the maximum possible efficiency of a heat engine given the temperatures of the reservoirs. Essentially, the amount of heat taken from the hot reservoir divided by the temperature of that reservoir is equivalent to the amount of heat given to the cold reservoir divided by the temperature of the cold reservoir. But even in its idealized state, this could never yield perfect efficiency. So why not? The answer comes from the work of Rudolf Clausius. Clausius was born in what is now Poland in 1822. He attended a private school run by his father, and in 1844 he graduated from the University of Berlin after studying mathematics and physics. Only a few years later, in 1847, Clausius received his doctorate for studying the optical effects of Earth's atmosphere. His thesis proposed that the different colors we see in the sky is due to the refraction and reflection of sunlight. Clausius was appointed a professor at the Royal Artillery and Engineering School in Berlin. It was here where he published his most famous paper, On the Moving Force of Heat and the Laws of Heat which may be deduced therefrom. Banger of a title. It was this paper where Clausius pointed out contradictions between Carnot's principles and the concept of conservation of energy, and I'll come back to this in a bit. From 1855 to 1867, Clausius served as a professor of physics in Zurich. It was here where he greatly contributed to many molecular physics problems of the time. His work greatly expanded the kinetic theory of gases and laid the theoretical foundation that explained the translational, rotational, and vibrational movement of molecules. In 1870, Clausius organized an ambulance corps that served during the Franco-Prussian War. It was here where Clausius was wounded in battle and left with a lasting disability. After his wife died in childbirth, Clausius had to scale back his research to focus on his health concerns and his parenting responsibilities. Rudolf Clausius died in 1888. Now, how exactly did Clausius contribute to entropy? Well, it goes back to that paper I mentioned earlier, the one where he points out contradictions between Carnot's principles and the concept of conservation of energy, essentially saying that work which is produced by heat will consume an equivalent amount of heat, and vice versa. Doing work can produce an equal amount of heat. It was in his 1854 memoir that Clausius ultimately explains why Carnot's heat engine can never be perfectly efficient. Clausius stated that heat will always flow from a hot body to a cold body, never the other way around. So even in its idealized state, there will always be some amount of heat lost to that cold reservoir, and that's why it's not perfectly efficient. In 1865, Clausius gave the first mathematical definition of entropy, as well as coining the term entropy. Clausius based the word off of the ancient Greek word for transformation, and wanted entropy to be similar in form to the word energy, since he believed the two quantities were intrinsically related. Clausius's mathematical definition defined entropy as the ratio of heat transferred over the temperature of the body. And given two temperatures, like the hot and cold reservoirs of Carnot's engine, one could use this ratio to determine the change in entropy of a system. This 1865 work also summarized the first two laws of thermodynamics. First, the energy of the universe is constant, and second, the entropy of the universe will tend to a maximum. I want to draw attention to the phrasing of these laws. Clausius described them in terms of the universe, which is the epitome of a closed, isolated system, but I'm getting ahead of myself. Finally, the last person I want to talk about in the development of entropy is Ludwig Boltzmann. Boltzmann was born in a suburb of Vienna, Austria in 1844. He then studied mathematics and physics at the University of Vienna and earned his doctorate in 1866. Boltzmann was appointed a professor of mathematical physics at the age of 25. It was here when he met his wife, Henriette. Henriette was an aspiring mathematics teacher, but was denied access to even unofficially audit lectures, since this was before women were allowed to attend Austrian universities. Boltzmann supported Henriette in her appeal of the decision and was ultimately successful. During his time as chair of experimental physics at the University of Graz, Boltzmann developed his statistical view of nature. This development came from his adopting of atomism, the belief that atoms and molecules exist. At the time, nearly all German physicists refused to accept atomic theory, so Boltzmann spent much of his final years defending his theories. In fact, Boltzmann had a long standing feud with the editor of a prominent German physics journal, who would only let him refer to atoms and molecules as convenient theoretical constructs. In May of 1906, Boltzmann was forced to resign his position as professor of theoretical physics at the University of Vienna due to his declining mental health. Only a few months later, he committed suicide by hanging himself. His symptoms seemed to indicate that he had what we now know as bipolar disorder. Boltzmann was buried in Vienna, his tombstone engraved with his now famous formula for entropy. So how did Boltzmann arrive at this famous equation? Well, it started when he was introduced to the kinetic theory of gases and the work of James Maxwell, who believed that temperature was a result of molecular collisions, and Boltzmann was inspired to bring statistics to the realm of thermodynamics. Boltzmann used Maxwell's statistical distribution of kinetic energy of molecules and expanded on it, creating the Maxwell-Boltzmann distribution as a description of molecular speed in gases. Boltzmann's key insight was that energy gets dispersed through a system over time, and this dispersion is due to the probability of a system taking on a given molecular state. See, with a given macro state, the state of a system as a whole, there are various microstates that can correspond to that macro state. Boltzmann deduced that a disordered microstate is far more likely than a perfectly ordered one. There might only be one ordered microstate for a given macrostate, but there can be trillions of microstates that are disordered that correspond to that macrostate. This leads to Boltzmann's equation for entropy. Entropy is the logarithm of the number of microstates, or the number of ways a system can be arranged, multiplied by some proportionality constant. This constant now being known as Boltzmann's constant. And this is why many of you probably think of entropy as disorder or randomness. This is where people get confused about entropy. It's not disorder and randomness as we usually think about them. It's statistical randomness leading to disordered microstates being more probable than ordered ones. Picture a pair of dice, both set on 6. Now pick them up, roll the dice. What's the probability that they'll both land on 6? Not very likely, right? Well, add another die to that. What's the probability that all 3 dice land on 6? Keep adding dice, on and on and on, and the probability that they're all going to land on 6 becomes incredibly small until it's basically non-existent. Now, extend this to a system of atoms or molecules. There are a couple quintillion atoms in a single grain of sand. How many microstates can exist for that grain? For every atom, for every bond that exists, there might be several microstates that are equal in energy. The amount of microstates for that single grain of sand is so large that the human mind can barely comprehend a number that big. There's also another aspect of entropy that I feel a lot of people miss. I think most people are aware that the second law of thermodynamics states that entropy will always increase. What I think most people miss is that statement only applies to a closed, isolated system. And allow me to explain what I mean by closed and isolated. A closed system is one in which the amount of matter is fixed. Matter cannot come into the system, matter cannot leave the system. And isolated is much the same way except for heat. Heat can't flow into the system, heat can't flow out of the system. This is what I think people miss. I've often seen young Earth creationists try to use the second law of thermodynamics to disprove evolution, stating that how can something like life form while increasing entropy? What they fail to miss is that the Earth is not a closed system, and it sure as hell isn't isolated. We are constantly being bombarded by heat and energy from the sun. In fact, it's been hypothesized that life is a direct consequence of the second law of thermodynamics. Remember that as entropy increases, energy will become more dispersed, and life is very good at doing that. Think about how we're constantly emitting body heat. That's because the vast majority of our biological processes are exothermic. They give off heat, and that's going to increase entropy. A good metaphor for how complex systems can arise while still increasing entropy is mixing milk and tea. And brief aside here, I got this metaphor from the Veritasium video on entropy. I highly recommend checking it out when you're done watching this video, of course. The video goes into a lot more detail on the concepts and theory of entropy than I do here. As the milk and tea begin to mix, intricate and complex patterns begin to emerge before it becomes a uniform mixture. The universe can be thought of as the same way. We exist at a time when life is most likely to exist, but eventually all the energy in the universe will be evenly dispersed and nothing will be able to happen anymore because there's no free energy to use. This is often referred to as the heat death of the universe. When I first started conceptualizing this video, I quickly realized that I couldn't just talk about the science of entropy without it turning into a glorified lecture. So I decided to focus more on the scientists who contributed to our understanding of entropy. I decided to show the human side. I can't help but think about how Carnot died at the age of 36, never seeing how impactful his work would become, or how Boltzmann was stricken with worsening mental health to the point where he took his own life after spending his later years defending his theories to his colleagues who refused to believe him. But these men are remembered as some of the greatest scientists in history. They have equations and concepts and physical constants named after them. They sought to improve and expand the boundaries of human knowledge, and they did, even if they were never appreciated for it during their lives. So, what does this all have to do with the void I found myself in? Yeah, remember how I opened this video? Well, the second law of thermodynamics states that entropy will tend to a maximum. But we can decrease the entropy of a system if we increase it by an equal or greater amount somewhere else. My hypothesis is that when I stopped making videos after starting grad school, there was nothing to keep the void contained, so it just kept growing. But if I keep making videos now, I should be able to get the void under control and hopefully find a way out. I know that this video probably won't get as many views as some of my others. People don't really find entropy as interesting as I do. But I recently remembered how much I actually like making these videos. I find it fun and it's a good creative outlet for me. That's really why I do it. We exist at the time in the universe when life is most likely to exist. We are the swirling milk as it mixes with the tea. Carnot and Boltzmann might not have been recognized for their efforts during their lives, but their work was invaluable to our understanding of entropy. Maybe my videos will lead to something great, or maybe they'll fade into obscurity. Either way, I'm going to keep making them, even if it's just for me. So that brings us to the end of the video. If you made it through all of that, thank you so much for watching and sticking with me. If you're not already, go ahead and subscribe because you watched this whole video, so you probably like my content. And I will see you guys in the next video.